Hi, this is Russell Leidig with TigerSpike. This is an introduction to Karacell Encryption. Specifically, I'm talking about Karacell 3, which we just call Karacell. Karacell 1 was released in 2012, only in white paper form. Karacell 3 is the culmination of feedback that we received from the cryptology community combined with our own in-house performance optimizations and security enhancements. Karacell 2 was just an experiment. So like Karacell 1, it's a symmetric algo. So in other words, it's not for key exchange. It's not a replacement for RSA or elliptic curve. Key lengths of 121 to 512 bits are supported, such that key strength saturates at effectively 511 bits. We feel this is a minor security sacrifice in exchange for substantial performance gains. By design, it's immune to chosen plaintext attack, chiefly because Karacell involves generating XOR masks and XORing them onto plaintext to encrypt, and XORing them back off to decrypt. However, I should note that encryption and decryption are not totally symmetric because there is a header with some metadata and potentially a footer containing an encrypted hash. And specifically with regards to hashing, we support hashing of all the blocks. Blocks are 4 kilobytes, potentially less. We support hashing of all the blocks in parallel, as well as encryption of all the blocks in parallel. And then what's appended to the end of the file is actually the XOR of all the hashes of the blocks, which is then encrypted. And in fact, you don't need to use any hash at all if it's a situation where you feel that authentication is unnecessary. So that's purely an implementation decision, as is the choice of hash. The current reference code only supports 2 particular hashes, but that could be easily expanded in the future. So Karacell has been optimized for resistance to attack via quantum computer. And it turns out that this aspect of the design also hardens it against classical attacks. And by hard, I mean that for every bit of key, it's that much harder to attack Karacell versus AES, or frankly, other popular symmetric algos. And the main reason for this is the large amount of memory that's required in temporary space in order to mount a useful attack against Karacell, which wastes a lot of silicon that could otherwise be dedicated to logic units. It has been designed with multi-threading and GPU pipelining in mind. And it's very amenable to single instruction, multiple data type of execution, as we find in a modern post-microprocessor type of architecture. So there's a lot of parallelism available. And it's based on subset sum, which you can look up in Wikipedia. That's a NP-complete math problem. We feel it's important to build a crypto system around a known quote-unquote hard problem, as opposed to just creating something that looks like it might be complicated but may actually be weak. Subset sum and quantum resistance are related. That is quantum computing cracking resistance. The primary reason is that, as I mentioned, you have to devote a lot of silicon, in this case a lot of qubits, to storage of an uncompressible data table. And that data table we'll discuss a bit later, but it contains 2 to the 16th ones and zeros in equal amounts and in very random order. And the problem of memory size is exacerbated with quantum computers. And of course, as of the moment in 2013, no general purpose quantum computer yet exists, although a few special purpose ones have been built, most notably involving D-Wave out of Canada. And basically, quantum computers suffer from environmental interference in a very extreme, sensitive way. So that in the absence of quantum error correction, entanglement is very hard to sustain. So I suspect that Moore's law for qubit density, if quantum computers ever exist in a general purpose sense, that quantum Moore's law is going to be a lot slower than classical and perhaps not even exponential in nature. Quantum error correction could help in this regard, but I think it's pretty safe to assume that there's no better scenario than classical Moore's scaling, in which we have devices of such large scale, certainly in the past, less so at the current time, but in the past of such large scale that error correction was essentially unnecessary in many cases. So secondly, there are no known polytime algorithms for subset sum solution, even on a quantum computer, based on our current scan of the literature. And by the way, there's an asymmetric, that is a key exchange encryption algorithm based on subset sum, which was discovered by Lubashevsky, Palacio, and Segev in 2009. You can look up their paper. And they cite similar advantages in terms of the lack of a polytime solution. So, as I said, Karacell is based on subset sum. It's not literally subset sum. Technically, the subset sum question is just a yes-no question. Karacell involves some more complexity in certain ways and some simplifications in other ways. We hope it's close enough to still be NP, and as far as we can see, it is, but you're welcome to prove us wrong. So you're given the Karacell table, which, as I mentioned, is 202 to the 16th bits of public ones and zeros. It's just a big constant. So we then have 2 to the 16th possible tumblers, and you can think of these as tumblers on a briefcase that you can spin and select a number. So you can rotate this Karacell table by 2 to the 16th possible amounts. And by rotate, we're talking about rotating toward the least significant bit, that is rotating right. And each rotation is called a ring of k. We add the rings together as though they were integers to produce a Zor mask for encryption, that is encryption or decryption. And the mask is simply cut off if the message is actually shorter than a block. And a block is 2 to the 12th or 4096 bytes, and it is byte granular. So where do you get the tumblers to select the rings of k? So we have a 512-bit Marsaglia oscillator, that is a multiply with carry oscillator. You can Wikipedia for that. It generates up to 32 16-bit tumblers at a time. And the way it does this is we start out down here with the key, the initial value, and this is a used once value, and the block number. And they're iterated 10 times through this Marsaglia oscillator. And the result is 32 16-bit tumblers. Now, one of the great things about Marsaglia oscillators is that their period and their bit lane bias is pretty easy to predict. So in this case, the period is on the order of 10 to the 153rd. In fact, it can be computed exactly. And the maximum bit lane bias is on the order of 10 to the minus 68. So we think that's cryptographically safe amount of 0-1 bias. And so, by the way, if you need more than 32 tumblers, you just simply iterate the oscillator another 10 times, and another 10 times, etc., until you've generated all the tumblers you need in order to compute the mask for a block. And then on the next block, of course, the block number is different, so the tumbler set will be completely different. By the way, 10 times is not just an elegant number. It's actually optimal in the sense of entropy. And what we mean by entropy is defined if you Google for scintillating entropy test. You'll find my blog, leidic-message-digest.blogspot.com, which discusses that. And by the way, we screen the tumblers in order to discard repeats, which we think would weaken the modulo variety of subset sum that we've implemented. It might not, but the performance cost is small, and we'd rather be safe about things that we're not entirely sure about. So here's how modulo subset sum works. So you have this Karacell table. In this case, it's a 7-bit table. And you have some tumblers, 0, 4, and 6, and you have a message length, 5 bits. Now, of course, in reality, the message is byte granular, but you get the idea. So here is k, verbatim. Here is k rotated to the right by 1. You can see it's shifted right by 1, and then this 1 goes to the most significant bit here. And we rotate it by 1 again, all the way up through 6 times. And of course, you rotate it 7 times, you get the original thing. So these are all of the rotations we can come up with. Tumbler 0 is here, 0, 1, 2, 3, 4 is here, 5, and 6 is here. So when we add these selected tumblers together, we get this sum in binary. And then we modulo it down to the message length. So we chop off the bottom 5 bits in this case to form the mask of the sum and the number of bits. So what's the fastest classical attack on this system that we can find? Well, as far as we know, it's a special case of the Horowitz and Sani subset sum algorithm, which was produced in 1972. And this is despite recent advances in subset sum. There have been some significant advances in special cases that don't appear to apply to Karacell. This specific special case, which we call sparse Horowitz and Sani, runs in 2 to the 16th combination t divided by 2t combination t, given 2t tumblers. And by the way, the algorithm is actually quite a bit different than Horowitz and Sani, and perhaps we should call it the tiger spike algorithm, but there are nevertheless similarities, so we'd like to give them some credit. And we do, by the way, expand the tumbler count relative to the key length in order to compensate for anticipated sparse Horowitz and Sani attacks, such that trying every key would appear to be cheaper. So in other words, if you look at the raw amount of ones and zeros in all of the tumblers that we use, they're more than typically between 2 and 3 times as many bits as the number of bits in the key, because we're assuming that the search space is going to be shrunk by around this factor. So how does this work exactly? Well, here we have 2 to the 16th addends. These are just all the rings of K. And we're trying to find a subset of them, which when we add them up, produces the given mask that we have. And of course, this assumes that the hacker knows the number of rings that are involved because he knows the key length, and he also knows a piece of the mask that he could use to verify this analysis here. So in this case, we have 6 rings that we're adding together. And we could just take all possible combinations of 6 and look at the sums thereof and figure out which combination of 6 was responsible for the mask. And by the way, it might turn out that multiple combinations actually reproduce the mask fragment successfully, especially if it's a small mask fragment, in which case other filtering would need to occur. But there's an easier way to do this, inspired by the Horowitz and Sani approach to subset sum, which is we can cut this in half. So instead of looking at combinations of 6, we look at combinations of 3. So we find all the combinations of 3 in this particular list of addends. And this, again, is what gives rise to 2 to the 16th NCR 3 in this case. And we take all of those sums in this huge list, and there's a break here because this is much larger than the addend list, and we sort them least to greatest. And then what we do is we walk up from the bottom and walk down from the top in kind of a staggering way, and we try to find a set of 2 of these values that equals the mask fragment that we know. And of course, when we get to this point and this point, we'll find that this is in fact the correct set. Now again, there may be some sets that produce the correct sum for the known mask fragment, but then when we extend that sum to other parts of the rings and add them up, then we find that the resulting mask actually does not help us decrypt the rest of the block, so it would be wrong. And of course, there's a possibility, slim, but there is a possibility that these triplets will overlap. And of course, we don't allow that because we don't allow duplicated tumblers, so those would have to be filtered out as well. But that's the essence of the algorithm. Oh, and by the way, the denominator here, 2T NCRT, or 6 NCR3 in this case, is because there are 6 combination 3 ways, in this case, of discovering this set of 6 rings. Because, for example, we could have found this sum here and this sum here, right? There's a lot of different ways that that could occur. So we need to divide by that. All right, the fastest quantum attack would seem to have been developed by Bernstein, Jeffrey, Lange, and Muir this year in 2013. The complexity of this attack scales as roughly 2 to the 0.24 n. In other words, it's a bit faster than the square root of classical Horowitz and Sani for the general subset sum, and that is for n possible addends. But in Karacell, the addends are sparse. You're talking typically about tens of rings versus 10,000s of possible addends. So the sparse Horowitz and Sani algorithm that I just demonstrated seems to still prevail. So it's been conjectured that there might be a compressed sensing attack against Karacell. Compressed sensing is essentially the art and science of demonstrating that a signal which appears to be complicated, such as a sound wave, is actually very simple if represented in the right choice of orthobasis. And it's concerned with finding the simplest possible such representation. And if you look at the rings that are actually used in a Karacell situation, the rings are a sparse subset of all possible rings. So in this sense, it looks like a compressed sensing problem. So it's tempting to think that the standard compressed sensing toolkits might be of use. Specifically, we're talking about L1 norm minimization as relates to matrices. There's an algorithm that does this deterministically called homotopy, which I believe is also called Lars lasso. We might expect to find that quite helpful. However, it won't cut it in its existing form, nor will any other L1 minimization algorithm used for compressed sensing, because all of those algorithms presume that the coefficients of the addends are analog, but in this case, they're discrete. They can only be 1 or 0, and they're mostly 0. So there would have to be some kind of substantial modification to these algorithms in order to make them useful against Karacell. But it is a theoretical possibility. So key points. Quantum computers are an engineering problem, not a theoretical physics problem. In fact, there's a $100,000 outstanding prize for proving otherwise. So it would seem that it's a matter of time, decades perhaps, before this is a substantial threat to our existing crypto systems. And we need to do something about it preemptively. Extending key lengths, of course, is a possibility. The longer the key, the more difficult it is to crack, whether or not you have a quantum computer. But this overtaxes human memory, so effectively it's a non-solution, because then we spill over into things like USB sticks and removable storage and cloud storage, and open ourselves up to a host of other security problems, which might moot the significance of the encryption to begin with. So Karacell is a cheap, parallelizable, robust hedge against unexpected advances against the most popular algos. If you don't trust it, at least think of it as an insurance policy. You can always run Karacell on top of AES, on top of anything else you want. So if you'd like to contact us, you can reach us at karacell@tigerspike.com. I'm Russell Leidig, and this would not have happened without the great assistance of Stuart Christmas. That's all for now. Thank you.